Good morning students. Today we are going to discuss on the topic of electrostatics. So far we have learnt that electricity is the phenomenon of charges in motion. Let us question ourselves that there is no electricity without movement of charges. The answer is yes. There exists a concept of charges at rest, that is electrostatics. It is a study of charges at rest. The salient features are basic information, electrostatic induction, electrostatic field, electric potential, dielectric strength and capacitance. Now let us consider what are the features of basic information. Atom, ion, positive and negative charges, laws of electrostatics, definition of Coulomb, permittivity and problems. Let us discuss each step by step. First of all, what is positive, negative ion? Atom is electrically neutral, that is number of protons are equal to number of electrons. If atom possesses charge, then it is called ion. If the electrons are added or protons are removed, then negative charges are more than positive charges, then the atom now called as negative ion. If electrons are removed or protons are added, then positive charges are more than the negative charges, then the atom now called as positive ion. Positive ion, removal of electron or addition of proton. Negative ion, removal of proton or addition of electron. Next we will move into the laws of electrostatics. Coulomb is a scientist, has done very good job in electrostatics, which were promptly known as Coulomb's laws of electrostatics. Coulomb, it is the name of the scientist who found the electric charge. It is the basic unit for electrical charge. First law, like charges repel and unlike charges attract. Second law, the force of attraction or repulsion between 2 point charges is directly proportional to the product of their strengths and inversely proportional to the square of the distance between them. The mathematical treatment of this law as here F is proportional to Q1 Q2 and F is inversely proportional to d square, that is distance square. As a whole, F is proportional to Q1 Q2 by d square. This constant, this proportionality can be eliminated by a constant of proportionality k. Hence, F equal to k times Q1 Q2 by d square, where k equal to 1 by 4 pi epsilon, where epsilon equal to epsilon naught into epsilon r. Next we will see that what is Coulomb. It is a unit of charge. 1 Coulomb of charge when placed at a distance of 1 meter from the some charge will exert a force of 9 into 10 to the power of 9 newtons. Next we will see what is permittivity. Permittivity, which is basically the property of any material for passage of electrostatic lines. Epsilon naught, the absolute permittivity of free space, and its value equal to 8.854 into 10 to the power of minus 12. epsilon r, relative permittivity, it is the value which is changing from material to material. For example, for air epsilon r equal to 1. Finally, the force F equal to 1 by 4 pi into 8.854 into 10 to the power of minus 12 into q1 q2 by d square, that equal to 9.9 into 10 to the power of 9 q1 q2 by d square. Now we will discuss some problem. Calculate the distance between the separation between charges in vacuum, for which electric force between them is equal to the gravitational force between them on one of the at the earth surface. Mass of electron equal to 9.1 into e to the power of minus 31 kg. The charge of electron is equal to the 1.6 into e power minus 19. Solution. Gravitational force on the electron equal to mg newtons, that is 9.1 e power minus 31 into 9.81 newtons. Electrostatic force between them F equal to 9.9 into 10 to the power of minus 9 into q1 q2 by d square, thus 9 into 10 to the power of 9, 1.6 into 10 to the power of minus 19 e2 by d square. Gravitational force equal to the electrostatic force. By making these two equivalences, we will get d equal to 5.08 meters. Students, we will move into the next major subtopic, electrostatic induction. The phenomenon of an uncharged body getting charged merely by nearness of the charged body is called electrostatic induction. When a charged body K brought near to the uncharged body B, end of B near to A is negatively charged, and this charge is called bound charge, and other side is positively charged, and this charge is called free charge. Both this negative and positive charges are called as induced charges. If the body B is earthed with a wire, the positive charges going into the earth leaving negative charge behind. Next, if A is removed, this negative charge is also goes into the earth. It can be concluded as a positive charge induce negative charge and vice versa. Each of the induced charge is equal to the inducive charge. Students, we will move to the next major subtopic, electrostatic field. This topic is further subdivided as electrostatic field or lines of force, field patterns, electric field strength, flux density, Gauss law, distribution of charges, comparison of electrostatic and magnetic lines of force, and problems. Let us discuss each one by one. The first is electrostatic field or lines of force. Electrostatic field is defined as the region surrounding a charged body in which force acts in towards electric field or dielectric field or electrostatic field. This shows the force of repulsion or attraction of a unit charge. Lines of force can be defined as A line of force is the path along which a unit positive charge tend to move freely. The properties: emits from the positive charge and terminates at negative charge, leaves always normal to the surface, never intersect each other. These are imaginary lines. These are elastic in nature. Next we will move to the field patterns. The field patterns of the isolated charges are as shown in the first one, and the field patterns of the unlike charges are as shown in the second one. This is the field pattern of like charges. Next we will move to the field strength. The force experienced by a unit positive charge placed at a point is said to be field strength. E equal to F by Q, that equal to Q by 4 pi epsilon d square. It is equal to the force passing normally through a unit area at that point. Q by E, lines of force produced. E equal to Q by E by A, that equal to Q by AE, that equal to Q by A epsilon naught epsilon r newtons per coulomb. E equal to d by epsilon naught epsilon r, E equal to d by epsilon naught newtons per coulomb in air, where d is the flux density. Electric field intensity at any point in an electric field is equal to the potential gradient at that point. E equal to dV by dx. Next we will move to the flux and flux density. Now let us go for electric flux. Electric flux can be defined as the total number of lines of force emanating from a charge is called the electric flux. Number of lines emanating is nothing but total charge emanated. Electric flux psi equal to q coulombs. That flux density is the flux per unit area. T equal to psi by A or q by A. Next we will move to the Gauss law. The total electric flux through an imaginary closed surface or Gaussian surface is equal to the algebraic sum of the total charge enclosed in the surface of the charge, where psi equal to the sigma q. Let us see, in a region there are 5 charges are there: q1, q2, minus q3 plus q4 minus q5. The total charge equal to psi equal to q1 plus q2 plus of minus q3 plus q4 plus of minus q5. This can be said as sigma q. Next we will move to the distribution of charges. Let us go for the field distribution of the charges. How the charges are distributed. For hollow conductors, no charge resides inside. Here there is no charge inside the sphere. The total charge is distributed on the outer surface. Number 2, much charge will be found at the curvature. If you observe this curvature, the charge concentration is very much. Number 3, almost entire charge is concentrated at the edge. If you see these two sharp edges, this is one edge and this is one edge. All the total charge has been concentrated at these places. Next we will move to the comparison of electrostatic and magnetic lines of force. Let us see the comparison of the electrostatic lines of force magnetic lines of force. Due to charged body, it is due to current carrying conductor. Do not passes through the conductor substance, these will pass through the conductor substance. Do not form closed path, concentric in nature, from positive charge to negative charge, from north pole to south pole. Next we will move to the electrical potential. Every charged body has the capacity to do work by moving another charged body either by attraction or by repulsion. The ability of charged body to do work is its electric potential. It can be defined as the electric potential is it is the work done in bringing a unit positive charge from infinity to that point against electric field. Greater the charge on the body, greater its ability to do work and has more potential. Let us see what is the electric potential at a point. Let us calculate the potential of the charge q placed at a distance of d, this point. The force of attraction or repulsion between this can be unit positive charge, that is defined as UPC. F equal to q by 4 pi epsilon d square. The work done is equal to force into distance, where W equal to q by 4 pi epsilon d square into dl, where dl is the small elemental length taken. If we consider for full length, we have to integrate between the limits 0 to L, that W equal to integral 0 to L q by 4 pi epsilon d square into dl, that's equal to q by 4 pi epsilon d. Thus, the potential V equal to q by 4 pi epsilon d. Now, we will go for potential difference. When the potential of the two bodies are differ from one another, the difference in the energy levels is called potential difference. Let us calculate the potential difference. Consider 2 points A and B in the plane. Let the potentials be VA of one point, VB is another point. The potential difference VAB equal to VA minus VB. VA equal to q by 4 pi epsilon d1, VB equal to q by 4 pi epsilon d2, V equal to VA minus VB equal to, if you take out the q by 4 pi epsilon is a common, that into 1 by d1 minus 1 by d2. Let us see one problem on the slide presentation. Let us calculate one problem, that is evaluation of the potential or work done. Let us consider two positive charges 12 into 10 to the power of minus 10 coulombs and 8 into 10 to the power of minus 10 coulombs are 10 centimeters apart. What is the work done to be done to bring them into 4 centimeters closer? Solution. For this, one charge is to be fixed and the other you can see, that is the other charge is coming towards the fixed charge. If by that one, if 12 into 10 to the power of minus 10 coulombs is fixed, V1 equal to 9 into 10 to the power of 9 into 12 into 10 to the power of minus 10 by 0.1 equal to 108 volts. V2 equal to 9 into 10 to the power of e power 9 into 12 into 10 to the power of minus 12 by 0.06 equal to 180 volts. The potential difference is V2 minus V1 equal to 180 minus 108, that amounts 72 volts. The work done equal to charge into potential difference. The charge, now we have to take the charge of the second unit, that is 8 into 10 to the power of minus 10 into 72, it amounts 5.76 into 10 to the power of minus 8 joules. Students, let us move to next major subtopic, dielectric strength. Every electrical instrument or appliance is designed to operate at a certain rated voltage. If this voltage limit is exceeded, the material will lose its properties. This limit is called breakdown voltage or dielectric strength. Now, let us go for the definition of the dielectric strength. The voltage at which the dielectric material loses its insulating properties is called breakdown voltage or dielectric stress. Students, let us move to the next major subtopic, capacitance. We know that two conducting surfaces separated by a dielectric medium will constitute a capacitor. The property of this capacitor is to store energy, may be called as its capacitance. The amount of charge required to create a charge between its plates is called capacitance. That capacitance C equal to Q by V, that equal to charge per potential difference. 1 farad is too large for practical purposes. So, normally microfarads, that equal to 10 to the power of minus 6 farads, or nanofarad, that is 10 to the power of minus 9 farads are used. Let us see a simple calculation of capacitance. Let us calculate the capacitance. Let, for the sphere shown, R is the radius of the charged surface, Q is the charge, epsilon R is the relative permittivity, V equal to Q by 4 pi epsilon naught epsilon R, Q by V is the capacitance, that equal to 4 pi epsilon naught epsilon R, that is the capacitance. This value equal to 4 pi epsilon naught R in air, because air relative permittivity is 1. Here some types of capacitances are presented. Let us see the different types of capacitors. 1. Spherical capacitor. Number 2. Parallel plates capacitor. C. Multiple and variable capacitor. D. Cylindrical capacitor. Series parallel connection of capacitors. Let us see the effect of capacitance connected in series. Between A and B, 3 capacitance are connected. The equivalence of the capacitance 1 by C equivalent equal to 1 by C1 plus 1 by C2 plus 1 by C3. The C equivalent equal to C1 C2 C3 by C1 C2 plus C2 C3 plus C3 C1. If the same capacitances are connected in parallel C1 C2 C3 between A and B, the C equivalent equal to C1 plus C2 plus C3. Dear students, we almost come to the last resort of electrostatics. Now we have to observe the transient behavior of the capacitor. Transient means large magnitude in small time. Let us consider the transient behavior of the capacitor. Let us say the voltage V is applied across a capacitor which is connected in series a resistor R. When the switch is on, as per the KVL, V equal to Vc plus R into L dVc by dt. By solving it as a first order differential equation, results as Vc equal to V times 1 minus e power minus t by tau, where tau equal to Rc, where tau is called as time constant. Then IL load current, line current equal to C dVc by dt, that equal to V by R into e power minus t by tau, that equal to I naught into e power minus t by tau, where I naught equal to V by R. This is the maximum current. After mathematical treatment, its characteristic can be viewed as, if this current is plotted, it will show the characteristic like this, and the t can be called as the time constant, and it can be defined as the time taken by the voltage to reach 63.2% of the final value or 36.73 of the initial value. This is the transient behavior of a capacitor characteristic. Dear students, let us conclude our electrostatics. First of all, we have seen what is the electrostatics and what is the Coulomb's law, and then we defined, that is, what is the field lines and field patterns, and then we have seen what are the major subtopics in that one. As of that one, the potential is the very much importance in this one. Why? Because the electrical engineering is very much based on this potential, and then we went for the field strength, the dielectric strength, and then we defined the capacitance. The electrostatics is a very strong and powerful medium which will originated introduced into the field of electrical engineering is the capacitance. Why? Because some applications are required the utility of the capacitor. So, the capacitor, the basic theory behind the capacitor is nothing but electrostatics, and we have seen the, if the number of capacitors connected in series, what is the resultant? If the number of capacitors are connected in parallel, what is the resultant? We have seen. Finally, this presentation presented the transient behavior of the capacitor also. We have seen how the capacitor can be behave, what is the energy levels, how can it can be differed in the transient in nature, and the characteristic, how the orientation of the current is going through, either the current or voltage is passing through this capacitor. This is the summary. Thank you.
Further clarification, contact the Additional Secretary, State Board of Technical Education and Training, 7th floor, BRKR Bhavan, Tank Bund Road, Hyderabad 500063. Fax 040 322 0546.